Okay. Right. Welcome. Good afternoon, everyone. Welcome to the next Tuesday seminar at the Warsaw University Astronomical Observatory. And today we have a guest from Germany, Dominique Meyer, who's actually originally from France. And Dominique did his studies in Strasbourg, master in astrophysics and condensed matter physics. And then he moved for a PhD to University of Bonn, where he obtained his PhD cum laude in 2014, and then did his habilitation in Potsdam as well. Habilitation we know of very well here in Poland. Not everyone is aware of it, but we do it here as well. So he obtained his habilitation. Well, he's about to obtain his habilitation. Sorry, you've just submitted your habilitation. So best wishes for this. And that he did his postdocs in Tübingen or Exeter, and now is working in Potsdam. So, and Dominique is interested in circumstellar medium around massive stars, something what is related to things we do here, and we might find it extremely interesting. So, Dominique, the floor is yours, please.
Thank you very much for the introduction. So yes, this presentation is about the circumstellar medium of massive stars. I would like to show you an overview of what I'm doing, especially around evolved and dead massive stars. I also worked on star formation, but it will not be the case today. Let's go. And I hope it will trigger some questions. So don't hesitate to interrupt me if you have questions or any comments. Then I'll be very happy to answer. So if we start with the beginning, matter is, the universe is composed of galaxies, and our galaxy is the Milky Way. It is a spiral galaxy with a bulge in the center, as well as a couple of spiral arms. And we are located inside one of these arms. The Milky Way, or our galaxy, is composed of, essentially from the baryonic point of view, two elements: the stars and the interstellar medium. And actually, we define the interstellar medium as being everything in the galaxy except the stars. So this is the plasma in which stars are set, in which they born, live, and die. This figure, so let's concentrate now on the stars themselves. You probably know this famous distribution, the initial mass function, showing the occurrence or the number of stars at a given mass. So there's a lot of very small mass, very light and small mass stars. And then the distribution decreases as the mass of the star gets more and more important. And there is a clear separation between the low mass stars and the massive stars. So massive stars are defined. So the exact definition is that these are the stars which are going to finish their life as a neutron star or as a black hole. And it basically corresponds to the stars having an initial mass of 8 solar masses or more. So this is the vertical line I draw here. And they represent about 1% of all stars in the Milky Way, 99% of the others being stars like the Sun, a bit smaller or a bit larger. So these are the massive stars which we are interested in. Massive stars are extremely important. They are actually the most rock and roll objects in the universe. They are very rare, so 1% of all stars. Throughout their life, they blow very strong winds. The winds interact and completely smash their surroundings. Most of them die as a supernova. Some of them directly collapse as a black hole. And finally, they leave a huge imprint in their environment by the winds and also by the supernova ejecta when supernova happens. They are the objects synthesizing in their core heavy elements such as iron, carbon, oxygen, and so on, which will be released into the interstellar medium and propagated to the large distances from massive stars. So chemistry in the Milky Way strongly relies on massive stars, which acts as some kind of pumps in the cycle of material in the Milky Way. To make it a little bit clearer, we can summarize. In the galaxy, there are stars and there are the interstellar medium. So the interstellar medium is in yellow and the stars are in blue. Amongst the stars, there is the 1% of massive stars. And there is a region that is actually called the circumstellar medium and defined as being the region of the interstellar medium which evolution is governed by the feedback of massive stars. So where is it? It is simply around all massive stars. It is the direct surroundings of high mass stellar objects. And this region, this gas, follows an evolution that is different from the interstellar medium under the influence of stellar winds and stellar radiation. So once again, the circumstellar medium of massive stars. This is the subject of my, the common denominator of most of my projects, scientific projects. We can have an illustrative slide here. So you probably know that stars evolve. And in the case of massive stars, the evolution is very short, but very brutal. So typically, we have written here the typical evolution of a massive stars from the protophase. So when molecular cloud collapse, when a protostar is formed, they arrive to their main sequence where they spend most of their time. So this is a typical OB star. Then they all go to the supergiant. That's what we think nowadays. And then, so once they are supergiants, the mass loss rate and the wind properties change. It is denser and slower. And after, it depends on the mass. The heaviest the star, the more crazy will be the evolution. But it can also stop here. If a massive star is only 10 solar masses, basically we will have main sequence, supergiants, and supernova explosion. And to finish, the end of the star life, so the manner they cease to exist, is either the explosion, supernova plus a neutron star, that is left behind. The neutron star is really the remnant of the star, or they directly collapse as a black hole. And this black hole, the quest for stellar mass black holes is very trendy at the moment. I think you are also involved in it in Warsaw. And the different pictures that you see corresponds to how looks a typical circumstellar medium of the different phases that we discuss. So the protostar typically has a disk. These objects are only observed since about 3 to 5 years now, but they are a scaled up version of the planetary disks, like around our suns. They are just much bigger, much hotter, much darker. Main sequence stars, massive stars, have so powerful wind that they create wind bubbles. So huge parsec scale bubbles where the wind interacts with the interstellar medium. And if the star moves, the bubble is distorted as a bow shock. It's a very famous image here of the bow shock of Zeta Ophiuchi. Then, if the star evolves, new winds are released into these wind bubbles and it creates shells. This is a shell around a supergiant. This is a shell around a Wolf-Rayet. And finally, they finish their life as a supernova remnant, in the case they don't collapse as a black hole. And we have two pictures here. This is SN 1987A, so extragalactic remnant. This is the Crab Nebula, another remnant in which there is a neutron star. So what we have looked at is a typical evolution of a massive star completed with images of the typical evolution of its surroundings. As you can see, the surroundings of massive stars is directly, in terms of morphology and properties, connected to the evolution of the star itself. So by looking at the circumstellar medium, we have an image, we have to some extent the past fingerprint, the fingerprint of the past evolution of the star onto the interstellar medium. So that's why we can really, that's why it's important to look at it, what justifies its studies. What is the goal of our research, or what I would like to show you now is a journey through the evolution of the circumstellar medium of a massive star, starting from the interstellar medium. We are going to see the effect of the stellar wind. After the star's life, the effect of the supernovae ejecta. So we are going to concentrate on stars who do not collapse as a black hole. And finally, the effect of the pulsar wind. So the neutron star that is left behind a massive star is often rotating and called pulsars. The rotation of the magnetized pulsar creates a wind, which has effects on the evolution of the supernova remnant. So that's what we are going to do. And in terms of methods, I am doing numerical simulations. So I'm doing hydro and magneto-hydrodynamical simulations of stellar surroundings. So we start. As discussed before, the winds of massive stars interact with the interstellar medium, and these create an object called a wind bubble. This is the most famous picture of a wind bubble by Weaver in 1977. So here in the center is the star, and this is the medium. And essentially, the two interact here at a discontinuity, and different shocks are created. One is a reverse shock and one is a forward shock. So you have different layers and different conditions of temperatures, of densities, and also mixing of material happening at the discontinuity, because this is in reality Rayleigh-Taylor unstable. It's a very simplistic sketch. And the first level of complexity we can discuss is when the star moves. You know that stars are born in stellar clusters. They don't live alone. So the heaviest stars of the cluster are often catapulted out of their parent molecular cloud. And this makes about 25%, maybe 30 now, percent of massive stars runaway stars. So simply very fast moving objects. They move faster than the sound speed of the interstellar medium. Then what happens is exactly what happens when you shoot a bullet or when a plane travels faster than the sound speed. A bow shock is formed. In the left-hand sketch, we have a stellar wind bow shock. So the star is in the middle and goes downwards. it has exactly the same structure as the wind bubble. It's just distorted. And such objects are quite common around massive stars. We can observe them and learn a lot of information by looking at their shape, at their emission properties, and so on. The motion of massive stars is completely independent of the manner they will evolve. So actually, while moving very fast through the interstellar medium, they will continue the evolutionary sequence that we discussed. Main sequence, red supergiant, maybe more, and then the supernova explosion. We have here the density in a 2D simulation of an evolving star. The massive star is 10 solar mass star. And at the moment of the transition between main sequence and supergiant, the density of the wind will increase, but the velocity of the wind will decrease. And so this is a cartoon. It has to be read from top to bottom. You see here the bow shock, the large bow shock formed during the main sequence. And inside of this bow shock, there is a new wind, the supergiant wind, that is forming. So the black line is actually the discontinuity between the two winds. And our star is here, and it moves upwards. The velocity of the star is roughly Mach 1, so equal to the sound speed of the interstellar medium. And this shell is the newborn red supergiant wind. So at some point, the two structures will collide because the former bow shock is no more sustained by the winds of the previous phase, but the new structure is. And when they collide, we have this short-lived structure where new and former bow shock collide, and this is called the Napoleon's hat. So like this guy here, because it has the same shape. And finally, if you wait long enough, what will remain is only the bow shock around the evolved supergiant star. So this is the evolution of the circumstellar medium of a star leaving the main sequence and entering the red supergiant phase. Now let's concentrate on these bow shocks around evolved massive stars. That's how it looks. So these ones are true objects. Two bow shocks observed around supergiants. At the left, we have Betelgeuse. It's very famous because it is the closest in the constellation of Orion. So we cannot see the bow shock because it's infrared, but if we could, this arc would be as big as the moon, as the full moon. It's quite round here, quite circular. And the star moves this way, and it has some mysterious bar here. Nobody understands the origin of. At the right, we have IRC-10414. It's another, so it's much far away. Another moving star. So the black arrow is the motion of the direction of motion of the star, and the bow shock is there here. This circle here is the stellar wind bow shock. So we can just say a little bit parenthesis because the bow shocks have been detected by different manners. In the case of Betelgeuse, people simply looked at infrared image of Orion and found it. They were not particularly looking at it. It was a serendipitous discovery. In the case of the other star, people first looked at Gaia and also Hipparcos, so astrometric catalogs, And once they selected moving stars, they looked at the data. These data are optical. So they are from the H-alpha supercosmos survey, whereas the left data are infrared from Herschel. These objects are perfect playgrounds for numerical simulations. So we can try to model in the frame of the star how the wind will interact with the medium, and later tailor the models to these two images. That's how it looks. So this is a 3D model done with the Pluto code. Pluto is a free multi-purpose fluid dynamic code developed in Italy. And that's a model done with a Cartesian, so it's a box that is uniformly gridded. And the star is in the middle. The star is this red ball. And the bow shock is represented by the transparent surface. Now we have two series of lines. Yellow is the flow. No, sorry, yellow is the magnetic field. So the magnetic field of the medium that is considered as organized. In the middle, you can see the Parker spiral. So like our sun, there is a strong, the stronger component of the star is the toroidal one. So it creates a rolling of magnetic field lines around the star. And the red lines is the flow. So in the frame of the star moves this way. So in the frame of the star, it is equivalent of saying that a moving star has a moving flow in its own frame. So this is the flow of the interstellar medium. And these isotropic lines here are the red line is the stellar wind. So we can see how the wind penetrates the bow shock and is advected downstream. This is a typical model for the surroundings of supergiants. And it's quite interesting to, because it is 3D, we can play actually with the angle here. The angle between the direction of motion of the star and the angle of the direction of the local field. We can make the star moving along the field lines or perpendicular to them. And if you do so, so this is a cut through the density of similar simulation. The star is in the middle here, is the red cross. The red is the bow shock. The black line is the interface between wind and interstellar medium inside of the bow shock. So inside the black line, it's the wind, and outside it is the interstellar medium gas which penetrated through the bow shock. And the arrows, you can see the blue arrows, which are the gas. So it is isotropic around the star and organized in the interstellar medium. And the red lines is the magnetic field lines. And in one case, we consider that field lines and motion are parallel. And we got a very distorted bow shock. However, as soon as you assume that there is an angle between these two directions, this angle here, between this direction and this direction, you stabilize the structure. So you see no angle here between the red and the blue line arrows, and here some angle. When it's more than 5%, it's enough to stabilize the stellar wind bow shock. And it's a very important question, because the observations of bow shocks that we looked at, these ones, you can see that they are very smooth. However, early models of nebulae around supergiants were completely distorted. And this problem can be fixed considering the local orientation of the magnetic field. And to finish, you can simply play with the parameters and try to reproduce to find a snapshot that fits the data. So in these two images, we fitted so the color is the simulations with the star in the middle and the bow shock here, oops, and there. And the black contours are observations, so real data. For Betelgeuse here in infrared and for IRC in optical. And the blue line is an analytic solution. So this analytic solution fits very well the bow shock for one star, meaning that we are in a steady state. In the other, you can see that it's not the case. The bow shock is much more unrolled than the analytic solution, meaning that the star just entered the supergiant, that we are still almost in the case of the Napoleon's hat, and that this bow shock is very young. So this star is still evolving here. That's what we could say for two examples of circumstellar structures around evolved massive stars. So later, at the end of the star's life, as we discussed, the star will either explode with a core collapse, supernova, or it's going to completely disappear and collapse as a black hole. So how it looks once the star has collapsed, we don't know. But in the case it explodes and leaves a neutron star behind the progenitor, we speak in terms of supernova remnants. So a supernova remnants is the nebular leftover of dead stars, especially dead massive stars. There are different examples here. This is a very famous one, the Cygnus Loop. It looks like a droplet. And there are other remnants here. They have many shapes. There's a large variety of morphologies. And it's difficult to unify all these shapes and all these emission properties. So these objects are multi-messenger emitters. They emit by thermal emission, infrared, optical. They emit, obviously, they are a big contributor to the non-thermal cosmic ray. So they have non-thermal emissions, meaning they contribute to the cosmic ray spectrum of the galaxy. And we also know that they produce neutrinos, and since there is a neutron star, also gravitational waves. So there are many theories to try to explain the asymmetries of remnants, but obviously the one I am interested in is this one. Since we know that 30% or a significant proportion of massive stars move, and that their medium is shaped as a bow shock, the explosion doesn't happen in the middle of nowhere, but inside of the bow shock. And so eventually the supernova blast wave interacts with this bow shock. And if the bow shock is dense enough, if there is enough mass, it might be enough to deflect the propagation of the shock wave and to slow down it in the direction of the bow shock while to facilitate it in the other direction. And so finally, what we would get is an asymmetric remnant that is partly symmetric and partly not. It's a quite old theory, but only now computers permit to explore it efficiently. And that's an example of such object. So we can say a few words about it. This is the density field of the supernova remnant. So this drop generated by a moving massive star. So the star was in the middle here, was moving upwards. This discontinuity, this light discontinuity here and here is actually the bow shock from the supergiant star here, as it was at the end of the supergiant phase. And here in blue, we had the cavity that we can go back a bit, and this cavity here, you see, behind the stellar motion. So a large region where the gas has a density that is 1, 2, 3 orders of magnitude below that of the bow shock. So the propagation of the supernova blast wave, which started at the origin, was first isotropic, but then on the one hand, it interacted with the bow shock. On the other hand, it was just almost free to propagate downwards. And the interacting regions between circumstellar medium and supernova blast wave is here in dense, so it is this filament, either the walls of the cavity or the mushroom, because at some point the blast wave goes through the bow shock and propagates into the interstellar medium that is here and recovers the spherical shape. The vertical, the black arrows are the magnetic field lines, so organized in the interstellar medium and penetrating into the bow shock. So these models are 2D. This is why they look symmetric. And the two contours in black and in red and blue is they spot where the gas is made of 50% of ejecta, supernovae ejecta in red, and 50% of stellar wind in blue. And when they overlap in some regions, it means that there is a lot of mixing of material induced by the supernova remnant. So since the models include magnetic field, we can work out these models and calculate the emissivity for the synchrotron emission. So typically from the 2D model, you create a 3D object, consider a given line of sight, a given angle at which you want to see the object, and for each cell, you calculate the emissivity, which means you need the different quantities, but the most important is the component of the local magnetic field that is perpendicular to the line of sight. So this component here that is plotted in this image, and you see that it's not symmetric with respect to the line of sight. So this is why you have to reconstruct the 3D object and then to calculate this quantity everywhere. And once you have it, you project it, and from the cube you make a map. As a reconstruction tool, a projection tool, I used a code originally designed to make infrared images, so RADMC, and I modified it to read my emissivities so I can get images without having to to code myself my own projection routines and so on. So RADMC is also free. You can get it as well. So my fluid dynamics and radiation transfer codes are public. They are not mine, but I use public tools. That's what we have as in terms of results. So this image in black font and red color is how the remnant we discussed looks at different ages and different according to different viewing angles of the observers. And a variety of shape arises, so either rings or arcs. We also have horseshoes quite a lot, so bipolar shapes as well, and so on. So these synchrotron emissions are for radio, the radio waveband, and they can be compared, qualitatively compared with a couple of objects observed at the same waveband, like G296 or CTB109, and both the bipolar shape. So this one was a supergiant, and there is a neutron star in it, which has been detected, while this one has more like an half round geometry in one side and is more cut into the other side. This one also interacts with a molecular cloud, so that is not modeled into my simulations. But qualitatively, it was enough to validate the method I used for my simulations. So clearly, by considering the motion of the star, the bow shock it creates, exploding the circumstellar medium, you can get some interesting morphologies observed for supernova remnants of massive stars, simply as a result of the interaction between the ejecta and the stellar surroundings. And now we go to the last part. So we have discussed the effects of the winds interacting with the medium, and then the ejecta interacting with the winds interacting with the medium. Last step is the pulsar wind. So the neutron star left after the explosion of a massive star spins. It is highly magnetized and develop a leptonic wind, very powerful wind, that is going to interact with the ejecta, which are interacting with the stellar wind, which are interacting with the interstellar medium. The simulation we look at shows a cartoon where you can see the density fields of a 2D model. So this is why it's also symmetric. And it's a very simple initial condition because we put only the supernova blast wave and the pulsar wind. We completely neglected any effect of the winds shaped during the star's life. So the ejecta propagates, you have nice instabilities arising in supernova remnants, and in black we have the contour between pulsar wind and the other material. The pulsar wind nebulae forms. So what we see, the vertical lines, is the axis of rotation of the pulsar, and it has a very strong toroidal component, so this diamond shape is formed. This result for the pulsar wind is quite standard. It is well known that pulsars generate a jet with a disk in the middle. And this is, in the case, the medium is very symmetric, because the explosion and the interstellar medium are symmetric. Now we are going to do exactly the same thing but not forgetting to impose at the moment of the explosion all the circumstellar medium resulting from the interaction of the stellar wind with the environment. So this is the bow shock that we previously calculated. You can see the main sequence bow shock, the very long one, plus here around the shell, the bow shock from the supergiant phase. This is the cavity created by the motion of the star. Here the supernova ejecta, and then inside the pulsar wind. And you can see that the evolution is different. We have this drop-like shape. So this shape that we discussed here, we recover it. This is the supernova ejecta, but inside of it, the pulsar is also affected by the shape of the overall structure. And it develops differently in the north and in the south direction. Eventually, at longer time, it recovers this diamond shape with a disk and a jet, even though there still has differences in the north-south direction. So last thing I want to show you is a comparison between the evolution of the pulsars we discussed with stellar motion, so with the environment, and without. So these two figures show a synchrotron emission map calculated exactly the way we discussed before. Top is with stellar wind, without is without stellar wind, so just with ejecta and pulsar. In the case without wind, the development of the pulsar nebula is symmetric in the top-down directions, and we have this, the jet and the disk. The viewing angle is 45 degrees here. But in the case of the presence of a wind bubble that we don't see in synchrotron, so don't forget the synchrotron is dominated by the magnetic fields, and the fields in the stellar wind are not very important. So we don't see the wind itself, but the effect of the presence of the wind material onto the propagation of the shock wave, this droplet-like shape. And inside of it, the pulsar, but the pulsar will develop and shine differently in the two directions, north, south, here and there. It can actually be even screened under some conditions. So, general conclusion, the very last wind of a massive star, its pulsar wind, is still affected by its entire stellar wind history. So if we want realistic models for pulsar wind nebulae, we also have to consider the interaction of the main sequence wind at the onset of the star's life. So the understanding of the surroundings of massive star is a very interesting problem. And so far, what we can say is that none of the elements can be neglected. We have to start with a realistic medium, injecting it a realistic wind. Do that until the end of the star life, inject the ejecta, and finally consider the ultimate pulsar wind. That's the message I wanted to tell you. And now I am looking for, I thank you for your attention, of course, and I would be pleased to answer to questions.
Okay, thank you. Right, thank you very much, Dominique. That was very inspiring, and we have already some questions from the audience. Milena.
Thank you. Can you hear me?
So should I Wow, there's a lot of people.
I wanted to ask if, in terms of the first stage of evolution, as you said, so before supernova ejection, if we focus on the star itself, how much the rotation of the star affects stellar winds and then bow shocks? Is it a very local thing, or should we really also take that into account, looking not at ISM, but just at the rotation of the star?
That's something I worked on it last year only. Rotation changes how old the star will be when it will die. So a star with a massive star with rotation and the same without rotation will have a different fate. That's the way it will influence the surroundings. But now if you imagine, can you see my slides a bit?
Yes, we can see it.
The wind bubble from the main sequence is quite big. And the winds from the main sequence is generally symmetric. So asymmetries in the wind happen later in the evolved phase. And so it will have influences here in the middle. So it will not affect the shape of the overall circumstellar medium, but all the question is, when you have a symmetric wind or an asymmetric wind and then followed by a symmetric one, do you have, for example, a bipolar nebula? This is what I could show 2 years ago, looking at blue supergiant followed by Wolf-Rayet stars. And then you can shape something like a planetary nebulae, but with properties of massive stars. And is it enough to then affect, but it's small, no? It's less than a parsec. Is it enough to affect the propagation of the supernova blast wave? There's a Mexican paper claiming that yes. If you let me your name, I will send you the references.
Okay, so I will contact you after the seminar. Thank you.
Okay, thank you very much.
Right, any more questions from here? Beata, please.
Hello, thank you for the seminar. I just have a short question. Have you investigated how how binarity would influence these bow shocks and these circumstellar envelopes?
Yes, it's the same answer actually. So binarity will change the manner, will change stellar evolution, and actually the one of the manner to create asymmetric winds is when you have the binary, the companion rotating around a slow wind.
Okay, thank you.
And then the answer is the same answer as the previous question.
Okay, we see one question from Zoom. Marius, please.
Yes, hello. How you hear me?
Yes, I can.
Okay, thank you, Dominique, for your presentation. On your, exactly on that slide that I see on the screen here, yes, it is 25% of massive stars are moving fast. Yes, so my question is it possible to predict that after supernova explosion, remnants, like neutron stars or black holes, continue to moving fast as well? So this means that 25 or 1/4 population of remnants continue to moving fast, or on the similar speed, let's say.
Yeah. So no, because look, these bow shock moves with 20 to 70 kilometers per second. But then the blast wave The supernova blast wave is 30,000 kilometers per second. And eventually, this will grow, and completely embeds this region. So the blast wave is more powerful than the star. So we cannot say that, that's why I understand, but we cannot say that remnants are moving actually. Remnants are propagating and growing in size. But it will take a lot of time and they will be very big. At the moment, the blast wave will be slower than the stellar motion.
Okay, so this means that actually that this remnants like neutron stars, they generally losing the speed after supernova explosion.
Yes, it decreases with time. Yes.
So then not possible to expect that fast-moving neutron star.
This is the remnant.
Yeah.
Now, inside the remnant, there may be a neutron star.
Yes. So why interesting it is in this neutron star.
Actually. And the neutron star can be kicked by the explosion. And so there can be a runaway neutron star inside the remnant of a runaway massive star. In this model, you have a runaway massive star, but the neutron star was not moving. You can imagine that this pulsar is actually moving fast as well. Also making a bow shock. And at some point leaving even. Yes, in that case, if you speak in terms of motion of the neutron star, yes, the answer is yes. Because the explosion can give the neutron star very high kick of the orders of 1,000 kilometers per second. So this pulsar can leave and actually start moving into the interstellar medium. Yes.
Okay. Thank you, Dominique.
Thank you.
Marcin, please.
Hello. Thank you for your talk. I have a question. Which is related to this talk. Is it possible to somehow estimate the kick velocity analyzing the structure of the remnant?
I don't know, because the kick velocity relies on the power of the explosion. It depends also on the mass of the neutron star. Okay, that's okay. I don't know how to rely. No, I don't think, because a given star can move at different velocities, a given massive star. So you can have the same explosion of the same intensity. I mean, at the moment of the explosion and the moment of the production of the moving pulsar, there's no information about the circumstellar medium. So no information about the motion of the star. So I would say no. The only thing you can have sometimes is that when the pulsar leaves and goes out, it makes a hole in the blast wave, and you can see that. It just goes out. If you are lucky, you can. So the moving pulsars into these objects is my current topic. This is really something I'm interested in at the moment.
Analyze just neutron star, which we can see, and analyzing the whole remnant, which we cannot be sure what we kick velocity.
Sorry, I don't understand the question.
No, I just conclude that better to see neutron star itself, how and measure its velocity, than analyze the whole remnant.
Another thing is the neutron star can move very fast, like 1,000 kilometers per second, or it can move a bit slowly, 100, 200 kilometers per second. There is a distribution of possible velocities. And if it doesn't move too fast, it will still have the jet here. So this structure will be like this. While if it moves at 1,000 kilometers per second, it's a simple bow shock. You don't have this effect anymore, and that's something I look at the moment. So if you look at the shape of the tail, can you say something about the medium around? Yeah. But I'm new into neutron star. I didn't know anything at all about that.
Okay, I just have one last quick question. So you showed the beautiful bow shock of Betelgeuse, right? And it's a very nearby one and very fast one. But but the velocities, these are not like extremely extreme, right? We're talking about tens of kilometers per second, right? Is that enough to create bow shock? It means that many stars should have these bow shocks.
Yeah. I mean, if you have a density of 1 and a temperature of 8,000, so something inside an H2 region, so ionized by stars, the sound speed is 20 kilometers per second. So as soon as Betelgeuse moves at 29 or 30 kilometers per second, so it's okay for bow shock. Yes, there are catalogs of stars with bow shocks, thousands of hundreds now, of objects. Even the sun has a bow shock. We are living in a bow shock.
Okay, so it's not that uncommon. So you say that there are thousands of them known. That's great.
Yeah.
But they have to have enough stuff around so that there is a place where the bow shock can be created, right? It's not just a matter of velocity. You have to have a medium, right?
So the denser the medium, the easiest it is to make it.
Right.
But then it will be very small.
I see.
But it's not a question of place. It will just be smaller and smaller. That's it. Bow shocks are everywhere.
Okay, I think it's a perfect conclusion of your seminar here. So thank you very much, Dominique.
Thank you.
Thank you all for coming and joining, and goodbye.
Thank you very much for the invitation. I'm sorry I couldn't make it today. Really, I don't hesitate to contact me if you have questions.
Okay, I have your email, and I'm happy to share it with people who want it. Okay.
Thank you very much.
Thank you. Bye.
Goodbye.
The recording has stopped.
Right.